a standard question kids ask me about electrostatics is they say, Mr. Dewick, is this a tough unit? You guys always ask me that. And my response for this unit is, it depends if you keep up with the homework or not. If you try and cram this unit, it's going to be ugly. How ugly? Dylan shooting three-pointers ugly. Okay, yeah, that ugly. Okay?
It's 100%.
There's a reason he's only taken one. And the reason, Dylan, is this. This equation right here is the equation for force. This equation right here is the equation for potential energy. You may notice they look a lot alike. This equation here is the equation for electric field. It also has an E. This also has an E. You may notice they look a lot alike. This is the equation for voltage, which is also called potential. This is the equation for potential energy. You may notice they look a lot alike. The problem is, every year, I ask on the test kids to find, for example, Shashan, the electric potential energy, which is this. And they use that. And I have to give them 0. That's like if I asked you to find the acceleration and you gave me the length. Hey, you found the length correctly, but I'm sorry, I can't give you any marks for it. This happens over and over and over. So what am I going to try and do to combat that? First of all, I'm going to give you some advice that most of you won't take, and that is don't try and cram this unit. Keep up with the homework. But what I'm going to try and do is, and I'm going to encourage you to do, for the rest of this unit, get out your formula sheet. What I'm going to try and do is train your eyes to look in the right place, to look at the right equation right away. And well, I don't know. I'm grasping at straws, but it drives me crazy every year when I have a kid get 60% and on the written they got 3 things right, but they didn't find the right things, so I can't give them any marks for it. Okay? There's my little pre-warning. Having said that, if you keep up the homework, what we're going to be looking at is what's called electrostatics. Static electricity, how charges behave on the microscopic level. And as usual, I'm going to give you a great big review in Lesson 1. Lesson 1, Coulombs Law. We're going to start out with hopefully what you've learned as being obvious. Matter is made up of atoms. Last class I said you know this. Actually, you don't know this. We've told you this and you have to believe us. I don't think we've ever proved to you that matter is made up of atoms, but atomic theory does explain almost, well, everything that's going on. If you include quantum theory into it, it explains everything. Atoms are made up of particles. At the center of every atom, you have a nucleus made up of protons and neutrons. And I'm going to use the word that probably Mr. Perugia would hate, and rightly so. I'm going to say orbiting around the nucleus, you have electrons. Now, we don't like to use the word orbiting anymore because it implies that an electron is a little tiny particle like a planet, and that the orbits are what you think of as gravitational orbits. And that's not the case. What is an electron? So Graydon said that's a negatively charged subatomic particle. Not really. That's one model that we've given you, and that explains an awful lot. To be honest, if you ask someone who's getting their doctorate in physics, what's an electron? First of all, they're going to hum and haw for a while. The best definition is probably an electron is the answer to a probabilistic equation when you're trying to find the location of a certain amount of charge. You notice I didn't use the word particle. In fact, I told you it was an answer to an equation, which really, if you want what describes what fits everything, the quantum equation is the one thing that describes everything down to a T and doesn't have to have my famous, but everything I'm teaching you is garbage in my magic physics world. That's the one that works for everything. But it doesn't actually explain what an electron is. It just can tell you how it behaves and where it is and how to find it when. So what's an electron? It's a particle wave, because it's not just a particle, it has wave particles, it has particle wave duality. They're bizarre. And you're going to find when you get down to the quantum physics world, most of the rules that you think of as taking for granted as always working, don't. They don't. Are you doing a deja vu here? That's right, you are. Sorry, I just realized. Thank you. Good. Thanks for remembering. I would have forgotten temporarily, and then I would have yelled at you. Thank you for remembering. What we're interested in is the electrons. And for the purposes of my magic physics world, to make the math easy, I'm going to treat them like little particles that actually do orbit a nucleus, even though actually that's complete nonsense. It answers, it satisfies, it explains a bunch of stuff we're going to look at today. When atoms bind together to form solids, the electrons can be tightly bound to the atoms, like in covalent solids like glass. We call these insulators. Or they can be free to move around, like in metals. We call these conductors. The subatomic particles, like protons, electrons, and neutrons, have a property, and we've given this property a name. We've called it charge. And if you want to know what charge actually is, read up some quantum physics. It has to do with spin and all sorts of things. Anyways, we're just going to talk about it. It's charge that's responsible for electricity and magnetism. In fact, up until about 1870s, 1880s, it was thought that electricity was different from magnetism, but Faraday and a few others, Maxwell and other physicists, proved that electricity and magnetism are two sides of the same coin. And in fact, now we talk about electromagnetism. They're one and the same. They behave differently, but one causes the other, causes the other, causes the other, causes the other. Basic facts about charge. There are two types of charge. What do we call the two types of charge? You learned this in Science 9? Oh, come on, please. Positive and negative. They were so named by Ben Franklin, the American scientist slash politician. Sebastian, he named them wrong. It would have been much better if he called the electrons positive and the protons negative, because it is the electrons that are what's moving through all of our wires, or that what we're passing from object to object when we're giving something a shock. And it would be much nicer to talk about positive things moving. In fact, next unit, when we look at circuitry, you're going to find that on the first day I'm going to tell you, look, even though it's electrons that are negative that are moving in the wire, the math gets yucky. We're going to pretend that it's protons moving in the wire, because when an electron moves to the left, mathematically that's the same as a proton moving to the right. Even though that's not really happening, we're going to pretend that it happens because we want the math to be nice. He named them wrong, but we're stuck with it. Does anybody know what units charge is measured in? Volts is actually not. Volts is actually how much potential energy each amount of charge has. Volts is sort of equivalent to height on Earth when you drop something. An object that has a higher voltage is like lifting an object to a higher height. It'll do more damage. It can do more work. Amps is measuring current. Watts is actually measuring power. We've looked at that already. It's how much work you do in a given time. It's the rate of work. Coulombs, Jaron, thank you. Coulombs. Named after a scientist whose last name was? And the symbol? Capital C. The letter that we use for charge, we can't use the letter C, unfortunately. The letter C is taken. It's the speed of light, and that's such a fundamental constant of the universe, we're not going to muck around with that. And so the letter that we use for charge is Q. Ask your question. It's from a Latin word, I think, that means limit or speed. Can't remember, I have to go look it up. It's a C because not all physics was done by English-speaking people. In fact, not much physics was done by English-speaking people. What you really should be asking, Brett, is not why is it the letter C. What you should really be asking is why is charge represented by the letter Y? Well, it comes from another important quantity or quality of charge, and it's the fact that charge is quantized. It's where the word quantum physics comes from. When we talk about quantum physics, the word quantum means comes in chunks. For example, for the longest time, we thought that if you took a piece of matter and you sliced it in half, and then you sliced that piece in half, and then you sliced that piece in half, and you kept going and going and going and going, eventually you'd run into a piece of matter that was so small that it would keep sliding out from underneath your knife. For the longest time, we thought that was the atom. We said matter was quantized. It came in chunks called atoms. Afterwards, we learned that atoms were actually made up of three things. What three things? Protons, neutrons, and electrons. So then we said, okay, atoms are quantized. We think that's it. And we're going to stop there for the purposes of classical physics. Quantum physics came in and they said, actually, it turns out electrons and protons and neutrons are made up of smaller particles. Does anybody know what we call those? They're called quarks. I'll mention them briefly, but we're not going to use those. But the fact that matter is quantized, that charge is quantized, it comes in chunks, has some very, very profound and very, very bizarre effects. Let me give you an example. Pretend this golf ball is an electron. Which physicist was it? Not Bohr, not Heisenberg. No, it was in the 1820s. The name will come to me in a second. German guy. He was the one who realized that electrons could only exist in certain energy states. So we talked about electron orbits, even though that's a bad word. It'll do for what we're talking about. He said electrons can exist at this orbit because that's a particular energy state that they can exist in. Or they can be in this second shell, this second orbit, because that's a particular energy state that they can exist in. But they can't exist at any energy state in between. Now, here's what that means. It means if an electron goes from this shell to this shell, it has to teleport because it can't exist in the air. It can't exist at this energy state. It goes from here to here. It does not travel the distance in between. Can't exist in that distance in between. Teleportation on the quantum level, perfectly acceptable. In fact, not just perfectly acceptable, it's an immediate result of saying, well, if the electron can exist at this energy level, and it can exist at this energy level, but it can't exist at any energy level in between, how does it get from here to here? It doesn't. It exists here. This is why I said the best definition of an electron is a probability equation that best describes where its location is. Or it exists here. Can't exist here, so it can't travel the distance in between them. Okay? Shortest line between point A and point B is only true in our three-dimensional world, not on the quantum level. It gets a little weirder. We suspect that not just charge, that not just matter is quantized. We suspect time is quantized. We suspect that there is a smallest chunk of time, and just like the electron can't exist in this area where it goes from here to here, there is a chance that time can exist here. Nothing, the whole universe, including yourselves, winks out of existence in this section, and then blinks back into existence here, and then winks out of existence in this section, and then blinks back into existence here. And we would have no way of measuring it because we all wink out of existence too. It's possible. We could be blinking on and off. But because everything blinks on and off, including consciousness and any instruments that you would use to measure it, how would you know? In fact, because almost everything else seems to be quantized, it would be highly unlikely if time wasn't quantized. It would be one of the main things in the universe that wasn't suddenly behaving the way everything else was. As I said, universe is weird. So, what is the smallest charge? Well, in classical physics, the smallest charge was the charge on a proton or an electron. We call that the elementary charge. Afterwards, they did find out that protons and electrons can be broken down further into quarks. We're not going to talk about those. I'll mention it in a couple of minutes, but we're not going to do any calculations with those. The smallest unit, and this is on your formula sheet in the data section, 1.6 times 10 to the negative 19 coulombs. That's the charge on a proton. Oh, the charge on an electron, same thing, but negative.
We measure something like that. Why wouldn't we put Q?
Pardon me?
Why wouldn't we put Q there?
This is, we use the symbol E for the elementary charge. What we're saying is this is a charge, but by the way, the elementary charge on an electron or a proton is 1.6 times 10 to the negative 19. Find it on your formula sheet in the data section, just so you can see where it is. Thank you, Sam, for heeding my advice and finally getting out your formula sheet after my long rant at the beginning of this lesson. Okay? All other charges are multiples of that. Really, if you measure the charge of something very, 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 very accurately, and you divide it by 1.6 times 10 to the negative 19, you now know how many electrons are on there. Now, that's such a small number to measure anything that accurately. You asked, we'll talk how they actually did get it. They used what's called an oil experiment, and I'll show you a video of that a bit later, a couple of days. What that means, going back to your question, is any other charge, Q, is some multiple n of elementary charges. If you tell me how many electrons there are in an object, I can tell you what its charge is. Or how many protons there are in an object, I can tell you what its charge is. I multiply that number of protons, n, by 1.6 times 10 to the negative 19. Oh, and if it's electrons, I call it negative, even though they should be the other way around. I wrote here, technical comment, some of you will be aware of particles called quarks. So quarks do exist. They are what make up electrons and protons and neutrons. And quarks have charges of 2/3 of an elementary charge or 1/3 of an elementary charge. Meh, yucky math. In our magic physics world, we're going to pretend they don't exist. We're going to pretend, for the sake of nice math, that the smallest possible charge is this elementary charge. So in this course, I've given you a data page that lists the masses of the subatomic particles and the fundamental or elementary charge. So you have the elementary charge, 1.6 times 10 to the negative 19. Electron mass, really small, 9.11 times 10 to the negative 31 kilograms. A proton mass, 1.67 times 10 to the negative 27 kilograms. And then I don't think you have a neutron mass on your formula sheet. I included it here. You're not going to need it. If you are, I'll give it to you, but I don't think it'll ever come up. However, the data page does not explicitly list the charges, so you need to remember the following. Electron, negative or positive? How big? Elementary charge, 1.6 times 10 to the negative 19 coulombs. So you don't need to memorize the 1.6 times 10 to the negative 19, although most of you will because you get tired of looking it up. That's on your sheet. You do need to know that an electron is negative one of those. Oh, and a proton is positive one of those. And what's the charge on a neutron? Really? What's the charge on a neutron? 0. It's neutral. You need to know that. Turn the page. For a conductor, metals, electrons can flow freely and easily. Conductors are happy to pass one electron to another atom, to another atom, to another atom, to another atom. We're very happy to do that. For an insulator, the electrons cannot flow. However, Kevin, you can get the electron orbits to shift slightly. This is a phenomenon known as polarization. And then here's our key thought for the day. Charges exert a force on each other. Charges exert a force on each other. Let me give you an example. Like charges what? Unlike charges what? Like charges repel. Unlike charges. In other words, if I was drawing the forces here, they'd be pushing each other away. They'd be pulling each other in. Example 4 says, a negative rod is brought close to an insulating ball. The ball is first attracted and then repelled by the rod. Explain why this happens. How do you know it happens? Let's find out. How can we explain this? Well, we'll draw a little picture here. So at the beginning, the ball is neutrally charged. Now the ball really has millions, in fact probably trillions of electrons on it. I'm not going to draw that. For the sake of simplicity, I'm going to pretend that it's got one positive and one negative. It's neutral. But I do know that this rod has extra negatives because I rubbed some electrons onto it. As I come in close, what's going to happen? Like charges what? Unlike charges what? Like charges blank, unlike charges blank. Like charges repel, unlike charges. So what's going to happen is this negative charge is going to get repelled. This positive charge is going to get pulled towards it. We call this polarization. And so for a split second, roughly half of that ball, the closer half, the left-hand half, will be net positive, and the right-hand half will be net negative. And because the closer half, the left-hand half, is closer to the rod, it will exert a force. It will tug over. But as soon as they contact, this positive is going to pull over a couple of extra negatives from the rod. Why? Because unlike charges attract, and this rod has some extra electrons that it's willing to give away. And suddenly now that ball, instead of being neutral with a plus and a minus, has extra minuses, has extra negatives. So it's now negatively charged, as is the rod. Like charges do what? Repel. In fact, the like charges would repel in such a way they would probably force themselves to gather on the outside surface of the ball, because that's how they can get as far away as possible. We call this charging by conduction. The reason it's called charging by conduction is I had to physically touch it to apply a charge. The rod had to touch the ball, but then you suddenly saw the ball picked up a net charge and behaved differently. You can also charge by induction. Next page. Induction is when you charge up an object without coming into physical contact with it. How many of you have an electric toothbrush? Okay. I guarantee your electric toothbrush is an induced charger. If you take it off, look at the bottom, you won't see two pieces of metal and two pieces of metal at the bottom of your charger so that they come in contact with each other. Metal charges water, bad. You don't want metal charging around liquid. It uses what's called an induced charger. And in fact, coming on the market right now are induction pads for cell phones. You can charge up your cell phone if you buy an induction pad where all you do is you put your cell phone on the pad, you don't plug it in, and it induces a charge. Probably within 2 or 3 years, that'll be the standard. No, every cell phone will have a built-in induced charge system so that you don't have to plug them in anymore. Maybe not Apple, because they like to do their own thing. But okay. How can you induce a charge? Now, the systems that are occurring in your electric toothbrush or in an induced cell phone charger are more complicated, but I'm going to show you here at least one simple way where I can charge up two objects without actually physically touching them. I can induce a charge. How? So we're going to start out with two uncharged metal spheres. Again, they have trillions of electrons and trillions of protons. We're going to say they have 2 and 2 on each one, just to keep the math nice. Since they each have 2 protons and 2 electrons, they're neutral. What I'm going to do then is I'm going to bring in a negative rod closely. I'm not going to touch them, but I'm just going to bring the negative rod really, really close. And that negative rod is sending out an electric field in all directions. What's that electric field going to do? Well, the positives are going to want to get as close as they can to the electric field, to the negatives, because unlike charges attract. The negatives are going to want to get as far away as they can. So what you're going to end up with is more negatives in the further sphere and more positives in the closer sphere. With me so far, Zach? Then I'm going to temporarily freeze this. What I'm going to do is reach in, grab the bottom of this, and just slide it to the right. So we still have the negative rod here. We end up with that. Now if I remove the rod, look at that. Without actually physically touching them, I was able to charge one of the balls as positive and one of the spheres as negative. And I didn't come into physical contact. I got close, never touched. I induced a charge. That's a simple way to do it. There's all sorts of ways to do it, Nathaniel. That's not how your electric toothbrush does it. But at least it can be done. So hopefully I've convinced you with my little paper and plastic stick demo that there clearly is a force. You saw the paper leap up. You saw the ball move away from. There clearly is a force, and it acts in two directions. It can attract or it can repel. What is that force? What's the equation? How big is that force? This is Coulomb's law. So Coulomb found this. We'll call it Fe for electric force, just like we called it Fg for gravitational force, or Fn for normal force, or F friction for friction force. And it depends on two things. Charge 1 and charge 2, how big the charges are. That's the first thing it depends on. Divided by the distance between them squared. Oh, but Austin, this is going to give you coulombs per meters squared. If I want an actual answer in newtons, I need to put a constant right there, just like, oh, what equation does that look an awful lot like, actually? Gravity, doesn't it? You're not the first ones to notice that. You won't be the last ones to notice that. Coulomb knows that. Any physicists coming after have noticed that. And they've asked a couple of logical questions. First question they've asked is, well, if the equations look so darn much alike, maybe they're a subpart of some bigger universal equation that describes everything. Einstein spent the final 40 years of his life looking for this. It's called the theory of everything, TOE, or the grand unification theory, GUT. But you wanted to find one equation to bind them all, one equation to rule them all. Because, I mean, doesn't that look like gravity? Different stuff, but it sure is similar. Haven't found it yet. String theory, maybe? Yeah, we haven't found it yet. That's the first question that kids often come up with. The second question that physicists asked is, hey, what are the two types of charges? No, what are the two types of charges? Positive and negative. Like charges, what? Repel. Unlike charges? Well, if this has two directions, why doesn't gravity have two directions? That's the next question people have asked. Well, if we can have like charges repelling and attracting, why can't we have anti-gravity? Why can't we have gravity repelling? Is that antimatter? Is that dark matter? We don't know yet. Win a Nobel Prize and find out. Oh, it's even weirder than that. I'll send you guys a talk via email just before spring break that'll wreck your whole spring break.
Is there a simple type answer like what's string theory?
Is there a simple type answer to like what's string theory? Ask me on a short lesson day. I have a 20-minute, 15-minute video that gives a reasonable explanation. To find the direction of the force, because force is a vector, we're going to use like charges blank, unlike charges. Like charges what? Repel. Unlike charges attract. To find the magnitude, oh, wait a minute. I forgot to tell you. G was 6.67 times 10 to the negative 11. What's K? It's on your formula sheet. Go find it. It's a fairly easy one to remember, actually.
9 times 10 to the 9.
Alejandro, what's K?
Just wrote it down. Busted.
9 times 10 to the what? What was big G? 6.67 times 10 to the what? I tried to convince you that gravity was a really, really small force. Hopefully, look, electricity, we need a 10 to the 9th to get the numbers into newtons. Gravity, we need a 10 to the negative 11. Gravity is by far the weakest force of the big four fundamental forces, by far. You just think it's big because it dominates your life because the Earth is huge. Oh, actually, no. I was able to defy gravity with about 5 seconds of effort there with a ruler which had barely any charge to it. That was able to lift a piece of paper off the ground easily. Gravity's weak.
If you did that enough, would the paper like stop giving a charge to the
Oh, I could probably, yeah, the more I add on there, the harder it is to add more and more charge. I imagine there's a saturation point where I could force more charge in, but not with just a simple rubbing system. Example 2. Find the direction of the electrical forces on the positive Q charge, the top left charge. You're going to be asked occasionally to deal with multi-charge diagrams. Multi-charge diagrams. And to do this, we're going to use something called, here's your fancy word of the day, the principle of superposition. Say, what? That's a fancy word for saying because our equation only deals with 2 charges, we're only going to deal with 2 at a time. What charge do we want to find the direction on? Top left. So don't write this down because I'm going to really muck up my diagram. Temporarily, Zach, pretend those don't exist. This is what the principle of superposition says. Do 2 at a time. Ask yourself, what direction is this charge exerting a force on that? Or in other words, this positive Q, is it getting pulled down or is it getting repelled up? What? Convince me. You're right. Okay. That's an unlike charge. So I would write down there's definitely a force that way. Let's write that in. Now we're temporarily going to ignore those 2. This is the principle of superposition. You do 2 at a time and pretend the other ones don't exist. Attract or repel to the right. Then attract or repel. Because that's the furthest away, I think I'll draw that vector the shortest. Make sense? Because the equation that I gave you did have an r in the bottom, just like gravity further away. Oh, and by the way, my fallback, Sebastian, for wrapping my brain around a lot of these is I'll temporarily pretend it's gravity, except the weakness is stuff can fall up in this model because it can repel. But if I'm trying to wrap my brain around what's going on, I'll pretend planet, moon, how would that behave? This should behave kind of similar. I got 3 vectors. How would I add 3 vectors together? Draw them. So I think it's going to look like this. Down, sideways, part ways back, but not all the way back, because that was a short vector. You know what my net resultant force is going to be? That. Not completely all the way diagonally down, but part of the way diagonally down, a smaller portion of it. Now, this is a very, very complicated situation because in real life, as soon as this started moving this way, well, the closer it gets to this guy down here, the stronger the repulsion gets, so it would slow down. It might hit like an equilibrium point somewhere in this area. I don't know. I'd really have to do some serious crunching. So, to solve force problems, here's what we're going to do. We're going to express charges in coulombs. Often they won't be given to you in coulombs. You'll see why in a second. We're going to substitute the charges and the distance into Coulombs Law. But to get the direction show, we're going to use like repel, unlike attract. Oh, although the charges are positive and negative, we're not going to put positive and negative numbers into our force equation. In other words, I don't want you to ever tell me the force is negative 89 newtons. Really, what a negative is telling you is you had unlike charges, they're attracted. Oh, or if you get a positive answer, it means you either had two negatives or two positives, they're repelling. And in fact, because we don't want you to put pluses and minuses in, sometimes you'll see the equation given with absolute value signs. I won't write it that way, but you may in some textbooks see it given that way. What they're saying is, don't be putting negatives and positives in. We'll decide the direction either beforehand or after the fact. Doesn't matter when. You can usually figure it out beforehand for that matter. Okay? So let's crunch some numbers. Example 3 says, find the force on the electron that's orbiting a helium, a positive helium ion that has a radius of that. Okay, and again, in real life, the electrons don't look like that, and they don't technically, we're in our magic physics world, keeping the math simple. They want you to find the force, electric force, is equal to K, Q1, Q2, over R squared. By the way, what path is this electron tracing out? A circle. What force is pulling it in a circle? Electricity. Are you saying, Mr. Duke, you could go Fe equals Fg and solve for V? No. Yes. No. This is again where the quantum world behaves strangely. And theoretically, yes. Realistically, actually, no, because they don't really travel in these kind of orbits the way we've drawn in our lovely Bohr model of an atom. What's K? 9 times 10 to the 9th. Charge 1 is the nucleus. What's in the nucleus? 2 neutrons. What are the charges on a neutron? 0. Oh, 2 protons. So it's going to be 2 times a proton. What's the charge on a proton? That's the elementary charge. 1.6 times 10 to negative 19. That's charge 1. Charge 2 is the electron. How many electrons? Just 1. What's the charge on an electron? Negative. I don't care about the negative. Elementary charge. I can see Brett's lips moving. Yeah, 1.6 times 10 to the negative 19. Divided by R. Oh, they gave it to me in the question. 2 times 10 to the negative 11 squared. How big is the electrical force? Nine times 10 to the 9th, 2 times 1.6. 1.6 times 10 to the negative 19 divided by 2 times 10 to the negative 11 squared. I get 1.152, oh, 3 sig figs, 1.15 times 10 to the negative 6. Is that right? Anybody else? Yu-Chen, yeah? Is that a big force or a small force, Yu-Chen? To the negative 6, big or small? Well, it's a small number. It's a huge force when you compare it to what it's acting on. I was bored, and so on the next page, I took the force on that electron and I divided it by the mass of the electron because I wanted to find the acceleration, and I know acceleration is force divided by mass. And when I did that, the mass of an electron is 9.11 times 10 to the negative 31. I got an acceleration of 1.26 times 10 to the 24th meters per second squared. So let me ask you this. Is that a small acceleration or a big acceleration? That's a huge acceleration. On the quantum level, it's a huge force. On the subatomic level, it's a massive force. We never got those answers dealing with gravity. In fact, we got 9.8, considerably smaller. So I'm trying to get you to get over this whole, in fact, you know, how big is this force? All of you do me a favor. Hopefully I've convinced you, Courtney, that this electric force that I've been yammering about is big. It's huge compared to gravity. Let's try one here, example 4. We want to find the net force, magnitude, and direction on the positive one. Okay, new symbol for you. 1 Coulomb of charge, just 1 Coulomb, is huge. In fact, if I had a metal ball with 1 Coulomb of charge and you touched it, probably it would kill you. So what you're going to find for this unit, almost all the time, we're going to give you charges in microcoulombs. The symbol for micro is this. This is micro. And when you see it, you can just replace it with a 10 to the negative 6. That symbol is on your formula sheet in that chart of all the prefixes. Joe, this is one time it's worth memorizing this one because you get tired of looking it up. So here's what it says. It says find the net electric force, magnitude, and direction on the positive 1 microcoulomb charge below. Which charge do they want me to find the force on? The left one, the middle one, or the right one? Let's call that charge 1. Unlike in masses where I tended to label stuff from left to right, usually I call charge 1 the one that I want to find the force on. Just makes sense to my brain. And now I'll call this one here charge 2 and charge 3. Emily, here's what we're going to do. We are going to again use the principle of superposition. Say what? Don't write this down. Temporarily, I'm going to pretend that that charge doesn't exist. Don't scribble it out. I'm going to find the force, magnitude, and direction between charge 1 and charge 2. Then, temporarily, I'm going to pretend that this charge doesn't exist. I'm going to find the force, magnitude, and direction between charge 1 and charge 3. Then I'll add them tip to tail. Although because they're in a nice straight line, I'm going to guess that I can just let one be positive, one be negative. If they're in opposite directions or if they're in the same direction, just add them up. By the way, I don't care about the forces between charge 2 and charge 3 because this question didn't ask that. This question just said find the forces on charge 1. There's 2. So I'm not going to find 3 forces, even though there are 3 forces overall in this diagram. I don't care about the third one. Is that all right? Okay, and I want to be, again, Dylan, maximum bang, minimum buck. So this is how I write this. Clarity, but not much work. F1, comma 2. What do you think that means? The force between charge 1 and charge 2. The force on charge 1 from charge 2. Whatever, but the force between those guys. And that's going to be K Q1 Q2 over R12 squared. The radius between 1 and 2. I'll be honest, sometimes I'll just put the R down there and just recognize that the radius is going to be different in the next section, but whatever. I'll be fussy and put a 1 and a 2 there. Alejandro, what's K?
9.79.
Thank you. Charge 1 is 1 microcoulomb. When you see the micro symbol, just replace it with a 10 to the negative 6. Charge 2, I know it's negative, but I'm not going to put the negative in here, is 2. No, charge 2, sorry, is 1 still. My bad, I'm looking at the wrong charge. Is also 1 microcoulomb divided by, how far apart are they? Don't say 20. Huh? 0.2, yes? They will feel free to give you distances in centimeters in this section. So meters, 0.2 squared. By the way, before I crunch the numbers, direction, please. So looking at charge 1, is charge 2 pulling it to the left or to the right? Left? So we can actually add the direction right now already. I can leave a space and I can write left. Okay, get the magnitude. I get 0.225. See if you get the same thing. Oh, another thing I should mention, Courtney, we're going to assume these charges are not much bigger than an electron, which means get the obvious one, gravity. Don't bother, because the gravitational force is going to be so small, who cares? So we're rarely going to include gravity unless the question clearly, specifically says that you need to. Is it 0.225? Anybody else? Now what? Find the force between 1 and 3. I'll change colors. That's going to be K Q1 Q3 over the radius between 1 and 3 squared. It's going to be 9 times 10 to the 9th. Charge 1 is still 1 microcoulomb. Charge 2 is 2 microcoulombs all over 0.1 squared. Oh, I can use almost the same stuff on my calculator. I just got to change 2 numbers. The second one becomes a 2, and the second 2 becomes a 1. I get a magnitude of 1.8 newtons. Direction. Which way is charge 3 acting on charge 1? Pulling it to the right or pushing it to the left? Unlike charges attract, this would be to the right. So here's the question. How would I add vectorially 1.8 newtons right plus 2.25 newtons left? In fact, you know what we're really doing? We're kind of doing a winner minus loser thingy here, aren't we? It's in a nice straight line. Now, what if they weren't in a straight line? Vectors. Add them tip to tail. We're going to do one like that in a little bit. On your test, tip to tail is fair game on the multiple choice. On the written, I'll keep everything in a nice straight line. Unless it's a scalar question, which is later on this unit for other stuff. I get 1.58, 1.575, but to 3 sig figs, 1.58 newtons to the right. You figured that okay? So more than one charge, straight line, Sam, not too big a deal. Example 4, turn the page. All right, a little thought experiment. At which point, approximately, could I put a positive 1 microcoulomb charge, so a positive 1 microcoulomb charge, so that it would experience no net force, so that if you added up all the forces at that location, they would be 0. I'll let you see if you can figure this one out. Location A, B, C, D, or E. In which of those could I put a positive 1 charge and have all the forces cancel? Shashan, you can't answer if you get help from Jaron. You know what? Let's see if we can reason our way there. When in doubt, let's try a process of elimination. Let's go try A. If A was correct, I'll just think about that temporarily. What direction is the force? Let's call this charge 1. Let's call this charge 2. What direction is the force from charge 1 on A? To the right or to the left? Good. To the right. Yes? What about the force from charge 2 on A? To the right? Can right plus right ever equal 0? Is that okay with that argument? You know what? Let's flip across to the other side and see if we can do the same argument for point E, because they look like they're mirror images of each other. Let's see. If this was correct, what direction would charge 2 be exerting a force on a positive charge sitting right there? To the left? What about charge 1? To the left? Can left plus left equals... Okay, so... Of the 3 remaining ones, which one stands out as being different? So let's look at C. Which way would charge 1 exert a force at location C? I think kind of that way. Which way would charge 2 exert a force on location C? I think that way. Now here's what I'm seeing. Charge 1 is to the left, charge 2 is to the right. That could certainly cancel out. But they both have a downward component, don't they? Can you ever go down plus down and get 0? So I'm looking at B or D. Which charge is bigger? Charge 1 or charge 2? So you know what? I said when in doubt, my fallback is I temporarily treat it like gravity. Let's pretend charge 2 temporarily if you wanted to find the point where the gravitational force of the moon exactly cancels out the gravitational force of the Earth, would you need to be closer to the moon or closer to the Earth? Why closer to the moon? Why would you need the radius smaller? Why would that? What's the difference between the Earth and the moon? What's the key? Okay, the mass. What's the difference between these two charges? Size? You know what? I think it would be there. Because just like you need to be closer to the moon than to the Earth to find that equilibrium point, I think you need to be closer to the smaller charge than to the bigger charge to find the equilibrium point. Oh, by the way, my Earth-Moon analogy worked because both the charges are negative, so they're both going to repel or attract. It says, explain your answer using appropriate concepts of physics. It's a little long, but that's probably how I'd answer it. I'd go through a process of elimination, so I'm not going to bother writing it out because we're getting close to the end and I want to finish example 5 and then turn you loose and show you a little video. Example 5. Find the electric force, magnitude, and direction on the electron shown below. Is this going to be in a nice straight line? We're going to be adding tip to tail. I'm going to call this charge 1 because it's 1 Coulomb. I'm going to call this charge 2 because it's 2 microcoulombs. And I'm actually going to call the electron E for electron. So I lied when I said I always call the thing that I'm finding the force on charge 1. It's electron. I'll call it E. But I'm going to use the same trick. I'm going to use this principle of superposition. I'm going to find the force, magnitude, and direction on the electron from charge 1. I'm going to find the force, magnitude, and direction on the electron from charge 2. I'll add them up vectorially. Let's find the force, magnitude, and direction on the electron from charge 1. That's going to be K, Q1, QE over R squared. It's going to be, Alejandro, K is 9 times 10 to the 9. Charge 1, 1 microcoulomb. Charge 2, it's an electron. On your formula sheet, 1.6 times 10 to the negative 19. All over 2 squared. Ah! Those aren't meters. What are they really? So it's going to be 2 times 10 to the negative 6 squared. These things are really close together. What do you get? You'll never know. I remembered last class. This time it was accidental. You get 3.6 times 10 to the negative 4? Direction. You know what? Let's go, since we're going to be doing some trig, how about we go north, east, south, and west, and we can use our what of what. Direction, north or south? That electron, is it getting pulled down or is it getting pushed up? I'll write the word south because I'm worried if I put an S, we'll think that's seconds for some reason. Now, let's find the charge between, the force between charge 2 and the electron. You know what, Courtney? I already have the equation. I'm going to take a gamble and see if I can go straight to numbers. If I can go 9 times 10 to the 9th, 2 times 10 to the negative 6, it's an electron. 1.6 times 10 to the negative 19 divided by 2 micrometers squared. You know what? I think I only got to change one number on my calculator, don't I? In fact, I think the answer is going to be 7.2, twice as big as 3.6. Yeah, 7.2 times 10 to the negative 4. Newtons. Direction. I don't think it's east because I think that's a negative charge, and I think negative charges would repel. I think the electron's going to get forced off. Mr. Marshall, I think it's going to go... Now what? Let's add these two together, tip to tail. So it's going to look like this. 3.6 times 10 to the negative 4 plus 7.2 times 10 to the negative 4. I think the resultant is going to be right there, with that angle right there. Hey, this is nice 90-degree trig.
Yeah, excuse the interruption. I'd just like to remind the grads that they're...
Sorry, guys. This went about 10 minutes longer than I wanted. I finished this in my other class, but I went off on a couple of tangents with you. I'll show you the answer to this tomorrow. Listen up. What's your homework, please? You can try number 1.
All students who bought a ticket to the
You can try number 2.
office at lunch.
You can try number 5. You can try number 7. Number 8. Number 10. Okay.
Yeah, right.